This video is part of a course on food physics. This porous media framework that we are in is part of the theory section of that food physics, and this subsection that we are in now belongs to the governing equations for transport. And the immediate preceding one was fluid flow equations. That is a separate video, and immediate following one would be the video on heat transport equations. We are going to derive the governing transport equations for each one of the phases of water, water vapor, and air. The governing equation for each one is derived by combining the conservation equation for each of the species and the transport rate laws. So the transport rate laws can be diffusive or diffusion-like, or the other group, as we have discussed in the past, would be convection or due to flow. We are still not going to porous media. Let's consider a simpler system like dye diffusion in water. And we are going to develop the conservation, the mass conservation equation for the dye right now. And then later we will extend this to porous media. So to develop this, we consider, let's say you can see these little dots in here, that's like the dye in water. And so we have a control volume that we set up, which is a fixed volume in space, and that is shown enlarged here. We're going to write the mass balance on this control volume. So note that the dye can come into the control volume by diffusion, and so that's the diffusive flux that we have derived earlier, or it can simply flow in, that would be the convection, and here is the convection flux. And these would come in and then they will go out. So if this is x, this is x plus delta x here, x plus delta x. So we write the mass balance this way. First of all, mass conservation says mass in to the control volume minus mass out plus mass generated should be equal to the change in mass stored. And so we write these mass in to the control volume on this phase coming in. I'm sorry for the messy writing with my mouse. The mass in would be the total of this flux. Remember, we had talked about total flux, diffusive plus convective, but for now we're going to just leave them as a symbol for total flux, which is NAX. So A is the species, X is the direction, so NAX is the total flux, so it's some kilograms per meter square per second. So I want to do a balance over some time delta t. So if NAX is kilograms per meter square per second, then the kilogram that comes into the control volume would be NAX multiplied by the area of this phase, which is delta y and delta z. That's here. So that's the amount, this whole thing is the amount that comes in over time delta t over the entire area, cross-sectional area. That's the amount that comes into the control volume. Then the amount going out would be the flux at the right location here, flux here, and multiplied by the same area, because the area of the face is the same and over the same time. So that takes care of the first two terms. Then there is generation. So what is the meaning of generation? RA is the generation per unit volume per unit time. So it's like kg per meter cube per second. Okay. So what is this generation thing? Suppose we are doing a balance for the dye. So if the dye degrades inside the control volume, then RA would be this loss, the degradation of dye kilograms per meter cube per second. That much would be gone. In that case, of course, it will be a negative value. So the amount of generation, if RA is measured in kilograms per meter cube per second, then amount of generation in the entire control volume, that's delta X, delta Y, delta Z, over time delta T, is going to be the kilograms that is generated. Now this in, out, and generation, the net effect of that is going to be change in the storage in this control volume. And how much is this change in storage? Suppose I designate Ca as concentration of the dyes, A being the dye, concentration of the dye. So concentration would normally be measured, let's say, kilogram per meter cube, and so then the amount, the change in the storage of dye in this control volume is going to be change in that concentration delta Ca multiplied by the volume. So this kilograms per meter cube multiplied by the meter cube would give me again kilograms. So every term now is in kilograms, and the equation is balanced. Note that I left them as total flux NAX. Rearranging the terms and dividing throughout by delta X, delta Y, delta Z, delta T, I get this equation. So the terms, the first two terms in and out, gives me this one, and then the RA term, and then the change in storage. So and then we make this delta X go to 0. So in the limit we get derivatives. So it's a differential equation instead of the algebraic equation that's this one is. So this is now a differential equation. See, the first term would be del X of NAX, meaning derivative of the flux, and then RA is the generation, and then del Ca del T is for the change in storage. So the reason we didn't put in flux term in here is, of course, we have not done porous media yet, but we're going to talk about multiple phases: water, vapor, air. For each one of them, the flux term has different mechanisms. So we're not going to put them now, but put them in context. When we are talking about water, we're going to put the transport mechanisms for water like that. The equation that we just derived is for a simple system, dye in the water. And we're going to now extend it somewhat informally to a multi-phase porous media situation and say the same equation is valid on the average. Okay, so we're going to extend it to this kind of a porous media situation. But this is a big jump. This is a big jump. The details of these are much complex and it's not appropriate to bring those in here. What is important to know is that these details showing the averaging, the fact that the equations now work for a porous medium on the average. This averaging process has been well documented and one can read up these details. When we apply to liquid in porous media, for example, the liquid in the porous matrix, then the liquid is really averaged over a representative elementary volume, or REV. These discussion about representative elementary volume, or REV, are in the first module of this porous media series. So the liquid in the matrix, as we talked about the concentration of liquid on the right, concentration of the dye in the liquid. Here we're talking about concentration of liquid in the porous media, and these two are going to be analogous. Likewise, we talk about vapor in space without the solid or the liquid, and that is also averaged over its representative elementary volume. And the air in the space without solid or liquid is also averaged over its representative elementary volume. So using these averages of the concentrations of liquid, vapor, and air, we can pretty much use the general equations, the conservation equations that we just derived. So now we write the conservation equation for each phase or component. And so we write one for liquid water, one for water vapor, and one for air. And so it's the same equation but written for different phase or component. Here C is the concentration, so this is Cw is concentration of liquid water, Cv is concentration of vapor, Ca is concentration of air, and Nw is the flux for water, Nv is the water vapor flux, and Na is the air flux. So these fluxes include diffusive and convective as present. We are keeping them implicit now because for each one of these phases the mechanisms are different. So we're going to bring those details together with the mechanisms. Then on the right hand side, for water we have minus I dot because water loses to vapor, so it's negative, and the same amount shows up in vapor. So in vapor it's a positive source term, and of course for air there is no generation in this case. So these equations have four unknowns: the concentrations, the three concentration, 1, 2, 3 concentrations, and I dot. Notice there's only three equations. So we need a separate equation for I dot, that is the evaporation inside the porous media. For this, we have a separate module on evaporation that provides all the details. So for now, we just leave them as I dot. Now for easier handling, this set of equations are slightly rewritten. So again, we have liquid, and for water vapor, they don't get changed. But for air, we combine vapor and air together and call it the gas phase equation. So you see, these two are the same, but this one got changed. So it's concentration of gas instead of air here. And the flux of gas, and so when you add them, because it's for vapor and air, there's an I dot that shows up. So these two equations are added in here. So as we further develop the equations, we will stay mechanistic. What this means is for each one of the phases, we will consider the actual mechanisms of transport, like capillarity, like gas pressure in this bread as a porous medium. And likewise for vapor, we will consider molecular diffusion or gas pressure. So for each phase, we'll consider the actual physical mechanism for it. So in using those mechanisms, we want to do a control volume analysis where we write equations for what's coming in and what's going out for each one of the phases: water, vapor, and air. So first we write this for the water phase. So each one of the mechanisms for water, there's four of them that we'll consider: capillarity, gas pressure, swelling pressure, and gravity. For each one of the mechanisms, we can consider in terms of a respective pressure. So these pressures, due to each one of the mechanisms, are added together. So let's look at them closely. So water pressure is equal to gas pressure. Gas pressure is something we're all familiar with. An extreme example would be how an egg would explode in microwave, because the evaporated water inside the egg that generates the pressure cannot get released easily, so it explodes. Then we have capillary pressure, like we're very familiar with, how water rises in a capillary tube, and in foods, of course, we have these pathways that have capillary rise. Then we have swelling pressure. Swelling pressure would be pressure that would be felt. For example, when the dried beans in water would swell and push the surrounding. So this becomes important in meat cooking as the meat shrinks with heat. Then, of course, there is gravity. So the point is, all of these four mechanisms are considered in terms of their respective pressures, and those pressures are added together, and we're going to write the equation in terms of this total pressure. So it's very hard to think of a situation where all four of those mechanisms would be present simultaneously. So we include or exclude the relevant pressures as needed for a particular process or type of processes. So we do this special case one where the matrix is unsaturated, so the capillary pressure is actually so much higher than that the swelling pressure and gravity driven flow can be ignored. This is not a very hypothetical situation. Most of the drying processes, for example, we dry to very low moisture content, and under those conditions the capillary pressure is really high, and compared to that most other pressures can be ignored. And so we write the water pressure to be made up of the gas pressure minus the capillary pressure. Note that the gas pressure has a positive sign in front, whereas the capillary pressure has a negative sign, because capillary pressure works as attraction to the matrix. So the sense of the capillary pressure is opposite of the gas pressure. So even if we have those two mechanisms, gas pressure and capillarity, it's nice to have some idea of the relative importance of those two transport mechanisms. These kinds of information are hard to come by. So from the literature, we could locate several studies, research studies, where this capillarity and gas pressure is included. For example, for microwave heating of food, puffing of food, microwave drying, and frying, and bread baking. So all of these have capillarity and gas pressure in their formulation, but it is still hard to see from these studies. Unfortunately, there's no report on their relative importance. So I could find one study where the flux due to pressure driven, that's gas pressure driven, and capillarity have been compared. And so in this case, this is for the case of rice puffing. So you have high pressure gradients develop from inside of the rice to the outside, and the pressure driven flow and capillary diffusion, the fluxes due to them are somewhat comparable. It's just for that process. It will change very much for other processes. Recall the total flux is made up of diffusive and convective. As we apply this for water phase, what we just discussed is the mechanisms for water transport are those four pressures. So we think of water transport as due to flow from those four pressures, and of course we're using only two of them here, the gas pressure and the capillarity. So because it's thought in terms of a flow, then in the mass flux equation, the diffusive term completely drops out. So we only have the convective term. Now, of course, let's look at dropping of the diffusive term. We all see very easily that water doesn't move by molecular diffusion. But how about capillarity? So to start with, capillarity is something we are thinking in terms of capillary pressure or flow due to capillarity is part of capillarity is part of flow. So that is included in this U. And so we're going to get the velocity of water using Darcy's law, where this capillary pressure would be included. And here it is. The mass flux of water is written in terms of Darcy's law. This Darcy's law gives me the volumetric flux multiplied by the density. Note that the volumetric flux is written in terms of pressure in the water phase, which is made up of the gas and the capillarity. So we'll expand that in a second. And of course, to get numbers out, we also need these parameters: the permeability of water through the matrix and viscosity of water. So as I said, the water pressure is made up of gas pressure minus capillarity, because that's what we assumed earlier. So we then expand it out, so we get a term due to gas pressure if we expand out the derivative, and then we get a term due to capillary pressure. So you notice that these driving forces in the matrix, they're included in a very mechanistic way, like the gas pressure driven and the capillarity driven. So we're now going to consider the capillary pressure in more detail, but it is very important to know that so far anything we have done is clearly mechanistic and can be related to real physical processes for which parameters can be measured. So before I get started, I want to tell you that in this slide, first I'll confuse you a little, but hopefully it will be clarified later. So we're considering unsaturated flow, where capillary pressure kind of dominates. So under such conditions, for the flux due to capillarity can be written as this one, the mass flux. Okay, and now this term, so this comes straight from Darcy's law. This term can be rewritten because capillary pressure is a function of the moisture content. This can be seen in data. Unfortunately, we do not have this kind of data for food. So here is data from soils as porous media. So in the soil, you can see the capillary pressure really increases. It's always negative. So this negative, the magnitude of it increases as you take water out. So as you take water out, the capillary pressure increases, and it's very high value. Look at these numbers, very high values of capillary pressure. So then capillary pressure is very much a function of the water content, the moisture content, right? And so if PC is a function of the moisture content, then I should be able to write this derivative as a chain rule, that del PC del CW times del CW del X. Okay, if I do that, you notice that all of this stuff, I can call it this capillary diffusivity, and then this part is the good old concentration gradient. So remember how we did Fick's law. Fick's law is something multiplied by concentration gradient. So here for capillarity also we have something multiplied by the concentration gradient. So that something must be interpreted as capillary diffusivity. So if we write it this way, then we call this one as diffusivity. This, as I was promising, was the confusing part, that we really were thinking of capillarity to be included as flow, but now we are saying capillarity can be written in terms of a diffusive flux. So to clarify this further, you remember the two fluxes, a diffusive flux plus convective flux. So we started off this one with as the convective flux. So if it is not convective at the end, if it's diffusive, it doesn't change the overall situation for the total flux. So now, from now on, the capillary flux is going to be treated using this equation rather than Darcy's law, and then this equation follows the diffusion pattern. So the mass flux for unsaturated flow, that's very important. This discussion is about unsaturated flow. So the mass flux can be written as due to gas pressure and due to capillary pressure. However, we just showed that the capillary flux can be rewritten in terms of some quantity on the left, which can be thought of as capillary diffusivity times concentration gradient. So what this means is the mass flux of water, which was thought in terms of a flow due to gas pressure and flow due to capillarity, can now be rewritten slightly in terms of flow due to gas pressure. So you still have a velocity that is due to gas pressure, but the capillary part I'm writing in terms of a diffusivity. So the diffusivity is of course defined in terms of a negative of that quantity, and so we have the convective flux and diffusive flux. This is what I was saying could be confusing initially, because capillarity, we kept saying flow, but it doesn't matter because this is the total flux. So one term happens to be looking like a diffusive flux now, even though we started from convective flux. So we're going to now substitute the flux equation that we just wrote for mass flux into the mass conservation equation for water to get the transport equation for water. So we substitute that in the mass conservation equation for water. Remember, this was the equation for water in which we substitute for this flux. It's actually a vector, but we are writing in a scalar way, kind of sloppily. So we substitute for the flux the quantity. This is what we substitute, and then we simplify. Del x, this term becomes here, and this guy we move to the other side and rearrange, and we still have that evaporation term I dot. So you notice this equation is very much like the transport equation that we always see, right? It's something we always see, except that it has different interpretations. So UW here is superficial velocity of water through the porous matrix, and concentration of water is an average of how much water is there per meter cube, but over this averaged over the representative elementary volume. So the equation looks similar, but the quantities are interpreted differently, and we have to remember that. So this was nicely, for our ease, we derived this for single phase. So if we generalize this to higher dimensions, then we can write more in the vector form. And again, if you recall, this is the storage term. And then this is the term due to flow, and this is the term due to diffusion. So the diffusion here is capillary diffusion, and this is the evaporation in the matrix. So eventually we solve this equation for this saturation of water. So I used relationships that have been derived elsewhere. Concentration can be written in terms of density, saturation, and porosity. These relationships would have to be looked up elsewhere, but eventually this equation is solved for the saturation of water. So we summarize this equation for water transport for the special case when swelling pressure is not important or gravity is not important, but this is applicable to many different situations. So for that, if we summarize using this picture we had before, where total transport is divided into diffusion-like or convection-like. In case of water, then we have the convection or the gas pressure driven flow. That would be the convection part, and then the capillarity, which we started off is looking like convection, then we moved it into diffusion for this special case of unsaturated flow where the capillary pressures are quite high, and therefore capillarity can be written as diffusion-like. So you have one that is diffusion-like and the other that is flow-like. Together it makes up for the transport of water through the food as porous media.